Okay, we're talking about planetary motion now. We've moved on. We're not talking about the Earth specifically. Now we're going larger scale. We're going to talk about our solar system to begin with. So go ahead and take out your Cornell notebook, set it up with Kepler's laws of planetary motion. And what we're going to do is we're going to use our understanding of Kepler's laws to answer questions about planetary motion. So this is Johannes Kepler. And he's the one that came up with these laws. He's a German astronomer, mathematician, and astrologer. And he lived from 1571 to 1630. So the question is, why do we care about planetary motion? Why is that important? Well, first, it allows us to detect the path of any incoming asteroids and predict when they're going to eventually hit us if they're in a certain orbit. It allows us to correctly determine the speed and location of planets for us to land on the moon or put rovers on other planets. So if you're an astronaut, you wouldn't want to be in a situation where they're just kind of guessing where to aim, right? You want them to be as confident as possible. And these laws allow them to be very confident in the location of the moon or landing rovers on Mars. We need to know that stuff in order to do that successfully. And then it allows us to discover black holes based on the star's motion around them. So if we can accurately predict the motion of a star or an object around another one, then we can place exactly where, let's say, a black hole that you can't see. We know exactly where it is because of these laws. So the first law is that the law of ellipses, all objects orbit the sun in elliptical paths. So they're not going around in just a circle around the sun. So what we see is that we have the sun here, that's one foci, or so one focus point. And then there's going to be an imaginary point across this line of symmetry going down the middle. There's nothing here, right? But it allows us to see and predict exactly what this path is going to be. So we have the sun here at one of the focus points. We have nothing at the other focus point. And then we have the planet that is going around the sun. The line that goes through both of the focus points, the foci, that's going to be the major axis. Eccentricity is what we're going to use to describe how elongated the orbital path is. It is the amount of flattening of an ellipse or how much the shape of an ellipse deviates from a perfect circle. And the eccentricity is going to be the focal distance, so the distance between that sun and the imaginary point, that distance divided by the length of the major axis. So if we go back, actually, it's going to be the distance between the sun and this point divided by the length of this entire line. If the eccentricity value is close to 0, it's going to be a perfect circle. If it is 0, it's going to be a perfect circle. As it gets closer to 1, it's going to be more of an ellipse. So if it was 1, if this was not 0.95, it was 1.0, it would just be a flat line because the focal distance would be the same as the major axis, creating a flat line. If in a circle, the reason it's a circle is because the focal distance, well, both foci are right there in the middle. So that's 0. So 0 divided by anything is going to end up being 0. 0.5 is somewhere right in the middle. So let's practice the problem really quick. I have this shape right here. We can have the two foci, and then we have our major axis. If the distance between the foci is 5 centimeters and the major axis all the way across is 8 centimeters, eccentricity is going to be 5 divided by 8. So I get an eccentricity of 0.625 for this shape. And this is moderately eccentric, right? So it's not close to 0, but it's not super close to 1. It's kind of right in the middle. Okay. Then here's a table with all the different planets and their eccentricities. You can see that they don't deviate that much from a perfect circle. The most eccentric is going to be Mercury here. And we'll be right back.